Math 1332, Chapter 10, Probability and Counting Techniques, Section 6, Odds and Expectation, Video 4, Expected Value of an Experiment. Now, in the previous videos, we learned about odds and the relationships to probability. And to summarize that, specifically, if you conduct an experiment that has a certain number of total outcomes, with a certain number of successes, desired outcomes, and failures, undesired outcomes, then the probability of a success is the total number of successes divided by the total number of outcomes. And it should be pointed out that you could also calculate the probability of a failure, which would be the number of failures divided by the total number of outcomes. The odds in favor of a success, whatever we put after that is deemed a success, is the ratio of the number of successes to the number of failures. And the odds against a success, again, whatever event or outcome is mentioned after the phrase odds against A, we deem a success. The odds against a success are the number of failures compared to the number of successes. But how can any of this be used in real life? Well, probabilities are used extensively in risk analysis, like when you're buying insurance, a primary component of risk management in business and insurance. They can also be used to make predictions about populations based on sample measurements. For example, if I wanted to know what percent of people are going to vote a certain way in a national election, I could survey 1,000 of them and come up with a percent of them that vote a certain way, and then use probability and statistics to make a prediction about the population. It's not an exact science, but it's pretty good. Odds, however, are used more for sports and specifically for sports betting or betting in general. I actually searched what are odds used for, and the primary results were for betting, for sports betting. So yeah, they're kind of gambling in nature. So you know what to expect here, not only in this video, but the next video. Now, this is nice, but what about the average person? Well, what about the average person? Well, about 46% of American adults engage in some sort of casino activity each year. Whether it's a table game like roulette, like you see in the forefront here, or some of these games back here. This appears to be a blackjack game. This looks like it might be a Mississippi stud game or a 3-card poker game. And of course, you got all your slot machines back there. So here's another roulette table. Somewhere off in the distance, there's probably a craps table and a lot of other games. If you've never been to a casino before, don't worry. I'll explain everything you need to know for the examples that we're going to look at. About 49% of Americans have played a lottery game, including this family that won $528.8 million, probably before taxes. And the Powerball looks like in January of 2016. So, where do odds and probability come into play? Well, they come into play into the calculation of something called expected value. Now, at its core, probability is a major component of games offered at a casino. When a casino offers a game, they need to make sure that in the long run they make a profit. Otherwise, they'd eventually lose all of their money. So yes, casino games are designed to make you lose in the long term. It's the short-term wins that keep people playing. Ooh, I won. Let's play some more. Keep playing and watch all your winnings evaporate. Math says it's going to happen unless you stop. Now, of course, casinos aren't the only place where knowing probability is key. Consider the following charity fundraising example. Have you ever had a kid try to sell things to raise funds for a school organization or something? The company that helps them with the fundraiser is in it to make money also. So it's all about who's getting good value, both the people providing the fundraising opportunity and the organization raising funds. So let's take a look at an example I made up. A local charity wants to hold a raffle to help raise money for the community. They set up a raffle where they sell 1,000 tickets at $5 per ticket. Once the tickets are sold, and that is supposed to say once, I'm not going to edit it right now. Once the tickets are sold, they draw 3 winners. The grand prize winner gets $2,000. The second prize winner gets $1,000. Third prize, $500. Yay! Make it rain. What is the expected value for the charity per ticket sold? And what is the expected value for a customer per ticket bought? In other words, expected value is exactly what it sounds like. It's the average value you can expect to gain or lose by selling or buying tickets or whatever the experiment is. For example, the person on the left represents the charity. I want to make money selling tickets. Person on the right represents the person playing. I want to make money buying tickets. Now, can the charity and everybody that buy tickets all make money? No, because the people that lose, the money that they lose is what the charity wins. Charity has to give away some money for an incentive to play. Otherwise, it would be just like, all right, 1,000 people donate $5 each, you get nothing. Incentive to buy is the prizes. Now, how do we calculate expected value, which is also known as just EV? When formatting dictates that I am going to use EV to represent expected value. Now, the answer to how to calculate expected value is pretty straightforward, although tricky to write as a formula. I'll describe how to calculate it, I'll show you the formula, and then you'll be thankful that we're not using the formula version. Now, in order to calculate expected value for an experiment, you need the following information. First, for each possible outcome in an experiment, what is the probability it will occur? Remember, an experiment is just a process that produces an individual result each time you conduct it. You roll a die, there are 6 outcomes, 1, 2, 3, 4, 5, or 6. You draw a card from a deck of cards, there are 52 outcomes, the 52 cards. Or if you draw a card from a deck of cards and I ask you its suit, there are 4 outcomes, spades, hearts, clubs, and diamonds. But for each possible outcome in an experiment, what is the probability it will occur? What fraction of the time do we expect it to happen? Also, for each possible outcome in an experiment, what is the value when it occurs? And this is why expected value is really used a lot in gambling scenarios, because there's a value for the person conducting the game, trying to make money by conducting the game. And there's a value for the person playing the game, the person trying to win money playing the game. Now, not everybody can win, so somebody's going to have a positive expected value. They expect to make money, and someone's going to have a negative expected value. They expect to lose money. In the battle of casino versus customer, guess who has the positive expected value, and guess who has the negative expected value? Now, once you have the answers to both questions for each possible outcome, those questions being, let's get this, use my little tool here. Here we go. The questions being, what is the probability it will occur? And what is the value when it occurs for each different outcome? But once you have the answers to both questions, here's what you do. First, you multiply each outcome's probability times its value. What's the probability that it's going to happen times what's the value when it does happen? And then you take the sum of all those products. So it's actually pretty straightforward once you gather the information. For every outcome, multiply its probability times its value, probability times value, probability times value, probability times value, and then you get these answers. And then you add them all up, and that's your expected value. Now, there's a formula for it. And if you were looking at expected value in a statistics class or a probability and statistics class, you would see something that looks like this. I'm not even going to go over what all these symbols mean. The capital EV does stand for expected value. The capital P does stand for probability, but the rest of it is just some notation to indicate that we're going to add a bunch of things. So it's more trouble than it's worth in this class to say, let's do this formula. But I wouldn't get hung up on this notation. Simply remember to multiply each outcome's probability times its value. That's what this chunk is saying. Then add up all the results. That's what this thing over here is saying. And that'll calculate the expected value. Let's go back to the charities raffle example. We're going to calculate the expected value per ticket sold by the charity. So I'm working the charity, I'm selling these tickets, and I'm wondering, on average, how much money are we making per ticket? Now, each of the tickets falls into one of four outcomes. Either a ticket wins the grand prize, which is $2,000, or a ticket wins second prize, which is $1,000, or a ticket wins third prize, which is $500, or, and most likely, a ticket wins nothing. You get $0. So for each of the outcomes, we're going to find its probability and its value. Let's start with a ticket wins the grand prize. Now, what is the probability that you get the grand prize winning ticket? Well, that's easy. There's one ticket that wins, but there's 1,000 tickets that are sold. So the probability that a ticket wins is 1 out of 1,000. What's the value of the winning ticket? And remember, we're looking at it from the charity's perspective. Let's think about this for a second. I sell this ticket, the charity makes $5. That ticket ends up winning. We owe you $2,000. 1 second, folks. Actually, let me finish this slide. We owe you $2,000. So would you say that the ticket that wins the grand prize is a positive value or a negative value for the charity? Well, since they made $5 but gave away 2,000, they're giving away way more than they got from that one ticket, so it's a negative value. Since the charity made $5 for selling the ticket, but awarded $2,000 to the winner, the value of the ticket to the charity is how much they brought in, $5, minus the $2,000 they had to give out. So the value of that ticket to the charity is negative $1,995. Of course, that's the ticket that gave away the most money. Outcome number 2, a ticket wins second prize, $1,000. Well, again, only one ticket is going to win second prize. So what's the probability? It's still 1 out of 1,000. But what's the value? Remember, the charity makes $5 by selling the ticket, but then has to give away $1,000 when person wins second prize. So since the charity made the $5 but awarded $1,000 to the winner, the value of the ticket to the charity is the $5 they made minus the $1,000 that they had to give away, for a net loss of $995. So negative 995. I'm eyeballing my cat off to the right, to my right. He's looking to pounce on my computer. I hope he does not. It'll be funny if he does. All right. Third outcome, a ticket wins third prize, $500. I bet you know how this is going to go. Probability, only one ticket wins third prize, so it's still 1 out of 1,000. What do you think the value of that ticket is to the charity? Think about it. Charity brings in $5 by selling the ticket and then gives away $500. So what's the value? Well, they brought in $5 but gave away $500. So the value of the ticket to the charity is $5 minus $500, which is negative $495. There's supposed to be another slide in there, but oh well. And if a ticket wins no prize, nothing. Well, the probability is 997 out of 1,000. Where did this come from? Where did this 997 come from? Well, they sold 1,000 tickets. One of them won the grand prize. One of them won second prize. One of them won third prize. Those are the only 3 tickets that won something. So the 997 comes from 1,000 minus 3. Now, what is the value to the charity of the losing ticket? It's not $0. The charity still made $5 for selling that ticket, but they don't have to give anyone any money for it because they didn't win. So the value of the ticket to the charity is the $5 they brought in minus 0 because they don't give away anything. It's a losing ticket. And so it's a positive value of $5. Now, we've calculated the probability and the value of all 4 different outcomes for this raffle. Here's a summary of those things. For the outcome of a grand prize, the probability was 1 in 1,000, and the value for the charity was negative $1,995. Remember, they made $5 and gave away $2,000. For second prize, same probability, but the value for the charity was negative $995. For third prize, the probability was the same, but the value to the charity was negative $495. They brought in $5 and then gave away $500. And then for no prize, the probability was 997 out of 1,000, and the value of those tickets to the charity was $5 each. Now, once the probability and value for all possible outcomes have been calculated, we simply multiply each outcome's probability times its value. So if we go back to this table, we would just multiply 1 over 1,000 times negative 1,995, and the same thing for every other row. I would expect to use a calculator to do this. Multiplying by fractions doesn't always come out well. Might as well resort to decimals. And here's the results of the probability times the value for each row. Probability times value for the grand prize is negative 1.995. Probability times value for second prize is negative 0.995. Probability times value for the third prize is negative 0.4995. Excuse me, negative 0.495. But probability times value for the no prize tickets is positive because the probability is positive, but so is the value for the charity. And when you multiply 997 over 1,000 times 5, you get 4.985. So we're almost there. The sum of the last column is the expected value of each ticket sold by the charity. In other words, if we add up that last column, negative $1.995 plus negative $0.995 plus negative $0.495 plus positive $4.985. That will give us the expected value of each ticket sold by the charity, and it ends up being a positive $1.50. Kind of makes sense that it's positive because the charity is trying to make money, so on average they should make a profit on each ticket. Expected value charity gains. I just said that from the sale of each ticket is $1.50. I know this seems like a long process to find the expected value, but it's actually much quicker than it looks. This is just the instructional side of it. You just need all of your probabilities and values, multiply each pair, and add. To demonstrate this, we're going to look real quickly from the other side of this charity, this raffle. What is the expected value for a customer per ticket bought? Remember, charities trying to make money by selling tickets. Customers try to make money by buying a ticket and winning. So there's an expected value there. What do you think it would be? The expected value per ticket for the charity was $1.50. Let's see what it is for the customer. This will be much easier because we have all the information we need. Neither the outcomes nor their probabilities will change. That's going to bother me. I know earlier I didn't edit something. Hold on. Earlier, I didn't edit something because I didn't want to stop in the middle of the video, but there's something that is inherently wrong here. I'll point out what it is real quick once I go back into the slideshow and share it with you because I know you can't see it right now. Right now, you just see me. And where did Zoom go? Zoom, zoom, zoom. There it is. And let's go back to here. Oh no, we started over. Fear not. Here it was. What's the expected value for a customer per ticket bought? This is much easier because we have all of the information we need. And here's where I had to make a very critical grammatical correction. Neither the outcome nor their probabilities. Where's my laser pointer? Laser. There you go. Neither the outcomes nor their probabilities will. That's supposed to say will change. Okay, you know what? We're just going to do this. Pen, please. That not shouldn't be there. There's too many negatives in the sentence. Neither the outcomes nor their probabilities will change. They will all stay the same. All right. Oh, I did fix it here. However, the values will change because we're now calculating the expected value for the customer buying a ticket instead of the charity selling the ticket. But there is a relationship between them, as you'll see momentarily. Here are the values for each outcome for the customer. Remember, They spend $5 per ticket, so that will be a negative value. I might win a prize, which would be a positive value. From the charity's perspective, when they sold a ticket, the $5 was a positive value. They were taking in $5, and the prizes were a negative value for the charity because they were losing money when they gave those prizes away. The grand prize value for the customer, they win $2,000, but they spent $5, which means the grand prize value of that ticket is $1,995. Think of it as the profit they make after they bought the ticket and won. Second prize value, they won 1,000, but they spent $5 to win it. So the value there is $995. Third prize value, they win 500, but spent $5 to win it. So the value there is $495. What's the value if they lose? Well, how much do they win? And how much do they spend? No prize value. They win nothing, but they spent $5 for the opportunity. And so that's a negative value for the customer. It's negative when you buy a ticket and don't win. You lost the money. Charity won the money. Now, did you notice the values of the outcomes for the customer are the exact opposite of the values for the outcome of the charity? Like, for example, for the charity, the grand prize winning ticket, their value was negative $1,995. And the reason for that is pretty easy to explain. It's because from the charity's perspective, the $5 was positive. They made $5. The $2,000 was negative. They gave away $2,000. And so when you turn the subtraction problem around, this becomes its opposite. So it's not a coincidence that the values for each outcome are the opposite for the customer, are the exact opposite of the values for the outcomes for the charity. And in any scenario, that will always be the case. What is a positive outcome for one is the same negative outcome for the other. Oh, I just pretty much said all that. Okay. All right, now you can set up the calculation for expected value in one expression. I know I'd set up a table earlier like I did over here. That was just to organize the information and kind of show you how everything was flowing. But the truth is, you can set it up in one fell swoop. There's really no need to, I mean, a table is good for organizing the information, but you can set up one expression to get right to the answer. Just remember that expected value is the sum, so it's an addition problem, of the products, so the sum of some multiplication problems of each outcome's probability and value. Here's the setup for the calculation for the expected value of a ticket for the customer buying it and trying to win. Notice the first multiplication. The 1 over 1,000 is the probability you win the grand prize. The $1,995 is the value of winning the grand prize. The second multiplication problem is the probability and the value of second prize plus the probability and the value of third prize plus the probability and value, which is negative in this case, of not winning. And if you do all the math, take a guess what it ends up being. Negative $1.50. Oh, wait a minute. The expected value for the charity for selling a ticket was $1.50 per ticket. The expected value for the customer buying a ticket is negative $1.50 per ticket. So on average, customer loses $1.50 per ticket. This makes sense because on average, the charity makes $1.50 per ticket. If you're wondering what I mean by on average, think of it this way. What if you bought all the tickets? Let's just talk this out. If I bought all 1,000 tickets, how much am I spending? They were $5 each, 1,000 tickets. I'm spending $5,000. How much will I win? Well, if I bought all the tickets, then I'm going to win all the prizes. I win the 2,000, the 1,000, and the 500, which is 3,500. So how did I come out if I buy all the tickets? Well, if I spend 5,000 and only win 3,500, if I subtract, I am down $1,500. I just lost $1,500 by buying all the tickets. But I bought 1,000 tickets. And if I take the negative $1,500 that I lost and divide it by 1,000, I get negative $1.50 on average is what I lost per ticket. So to summarize, here's how to find the expected value for an experiment. For each possible outcome, calculate its probability. That's usually a fraction. How many successes out of the total number of outcomes? For each possible outcome, calculate its value. How much do you stand to gain minus how much you lost? From the charity's perspective, it was a negative value when I sold a ticket but had to give a prize. It was a positive value when I sold a ticket and didn't have to give a prize. From the customer's perspective, it was a positive value when I bought a ticket and won a prize, and it was a negative value when I bought a ticket and didn't win. So for each possible outcome, calculate its value, multiply each outcome's probability times its value, and then simply add up all the products. This might be the last slide. I don't remember. It's not. Oh, in the next video, we'll look at one more expected value example that shows why casinos will, in the long run, always come out ahead on any game they offer. Come on in, relax, have fun. Maybe you win big. I remember what I wanted to mention. I thought about putting it in the video, and then I didn't. And it just popped into my mind here when I said that the expected value of a ticket for the customer buying the ticket trying to win was negative. Most of the time in state lotteries, it's a negative expected value game, meaning if you bought every single possible lottery ticket, which is almost physically impossible based on the number of tickets, you would lose despite winning every single prize because of how much you spent. But, and this is a true story, I heard it on the radio and then I looked it up. One time in the Texas lottery, not the Mega Millions, not the Powerball, the Texas lottery, where you have a lot fewer combinations of numbers to choose, the jackpot was high enough that if you bought every single possible ticket, you were going to make a profit. Well, when this happened, a group of investors got together, bought every single possible ticket. It was like 25 million tickets, won like 30 million, won like 60 million, plus all the smaller prizes. So normally the lottery is a negative expected value investment for the buyer unless the prize gets high enough. But then you have to buy all the tickets to guarantee a win, which is not very feasible, both for time and for money reasons. All right, that's enough. I'll see you in the next video.